Good morning. Today we study about hysteresis loop in a ferromagnetic material. See here. This is defined as the lag of change of magnetization beyond the variation of magnetic field. In the magnetic material, the induced magnetic flux density B, that is the B indicates the induced magnetic flux density of a material, lags behind the magnetization field H. H is nothing but applied magnetic field. Now, we consider a ferromagnetic material, just like take an iron piece. Initially it is not a magnetized. Now, our aim is to magnetize this iron material. Means our aim is to convert this iron into a magnetic material. Now, here we consider this magnetic material. Initially, it is a zero magnetization. Means the B is equal to 0 for this material, iron. If slowly we apply the magnetization field H to that particular material, then what happens means the magnetization will be gradually increasing. See, from this figure, here see, I will draw this diagram. See, let us consider from this figure, this graph. On x-axis we consider H and y-axis B. H is magnetic field induction, means field intensity, and B is the magnetic field induction. Now at zero field, initially the field means the iron material has no magnetization. The B is equal to 0 at H is equal to 0. Now we gradually increase the H value, then what happens? The B also increases. Means the iron will start magnetized. Means it becomes magnetized. At this particular point, say point A, what happens means it becomes a saturation. Means the maximum magnetization will take place at point A. Further, if we increase the H value, there is no change in B because it becomes a limited value. It becomes a limitation. So this point A is known as saturation magnetization, BS. Okay. Now we reduce this magnetic field H. Then what happens? Slowly the B value will be decreases. And even at zero field, we observe there is some magnetization, and it is denoted by BR, where BR is known as retentivity. Retentivity is nothing but even at zero magnetic field, we observe some magnetization. That is known as retentivity. Now, if you applied a negative magnetic field, H minus, as we decrease means if you increase the magnetic field in negative direction, we observe that the B value will be decreases. At this point C, we observe there is no magnetization, means the B becomes 0. At point C, the B becomes 0. And this point is denoted by HC, means cohesivity. Cohesivity means simply at negative electric field H, means the negative electric field has, what happens, the magnetization becomes completely 0 for the ferromagnetic material. That point is known as the cohesivity. If you further increase the H value, it will be reversely increases and it becomes a loop. So I draw a clear diagram here. See here. The curve will be in this form. See. At this point, when the H increases, it gradually increases and becomes the retentivity, and this is HC. HC is nothing but cohesivity, and reverse saturation magnetization, again it became saturation. This point D is nothing but reverse magnetization, means minus BX. Here the minus Br means the reverse in what is retentivity, and this point A is B, yes, means saturation magnetization. This is point B. At this point B is known as Br. Br is nothing but retentivity. That this point C, it is Hc, cohesivity, and this point E and this point F means the loop O, A, B, C, D, E, F, and A. This loop is known as hysteresis loop. This hysteresis loop is only done for the ferromagnetic material. Now we have go for this theory. Here, and then similarly, we have to. So here, I have given here the theoretical part. When H decreases and B also decreases, but is not becomes 0. At even a H is equal to 0, the B does not become 0. That point is known as retentivity. If you apply the negative magnetic field H, then at a particular negative value, the B becomes 0. See, minus H. That point is known as the cohesivity. And at point D, means further increase the H value in reverse direction. You observe where magnetization will be increased in the reverse direction, and this is known as negative saturation, becomes a negative saturation. And further, if you increase the positive direction, the path from A, D, E, F, A. Again, at point A, we observe a saturation, the positive. Their loop O, A, B, C, D, E, F is called the hysteresis loop. The area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization. This hysteresis gives the characterization of the ferromagnetic material. Means it may be a soft magnetic material or hard magnetic material. By using this hysteresis loop, the ferromagnetic material is classified into two types. That is hard magnetic material and soft magnetic material. If the loop area is more, then it is said to be a hard magnetic material. If the loop area is very less, and it is said to be a soft magnetic material. So here, in soft magnetic material, it is easily magnetized and easily demagnetized. Whereas in hard magnetic material, it is difficult to magnetize and difficult to demagnetize. This is the most important property of the ferromagnetic material, which gives the characteristics of this ferromagnetic.